So what we're going to be looking at here is we're going to be looking at the definition of an inner product space or inner product spaces. And that's really what the next set of lectures are going to be about. And what an inner product space is it's essentially a vector space. And it's a vector space with a set of different kind of set of calculations on it. All right. Or what we call a different set of operations. So when we think about vector spaces normally, and what we've seen with vector spaces already is that we have addition of the vectors, and then we also have scalar multiplication. And those are the things that allow us to create an algebra. And that algebra just means, like, how do we do all the operations on that vector space? And so we're going to continue to have those operations. We're going to continue to have vector addition and scalar multiplication. But what we're going to do is we're going to add in two operations. One of those operations is going to be called an inner product, and the other one is going to be called a norm. Now, you've seen both of these quite a lot, actually, inside of your multivariable calculus classes. So when we do multivariable calculus, we start out with this idea that we're going to take something called the dot product. And the dot product allows us to find the angles between vectors. It gives us important information about whether or not the vector is actually orthogonal, all sorts of those kinds of things. And that is an example of an inner product. It's not the only inner product, but it's an example of an inner product. And then in addition to that, we've got the thing called the magnitude, right, which is the length of the vector, and that's going to be something called a norm, all right? And so what you'll see is that mathematically we can actually define a lot of different kinds of inner products, and we're going to do that inside of this lecture. And also we can define a lot of different norms. That is, there's a lot of different ways to define magnitude, okay? And some of them make sense from the standpoint of it's like a distance, and others don't, okay? Like, for example, when we're working with functions, the idea that you're going to be actually calculating like the length of a set of functions doesn't really make a lot of sense. Okay, so consequently, we're going to get we're going to define the inner product mathematically in certain ways, and then we're going to define the norm in a set of ways. And what we want to do is we want to be really careful about how we actually make these definitions. So we're going to begin with, we've got this inner product space. This object, it's a vector space V that will have these two extra operations defined on it. One called an inner product, the second called a norm. Now, let's look at the standard inner product. And you've seen this a lot, like I said, inside of your multivariable calculus class. It is the dot product. And we can talk about the dot product from the perspective of a lot of different spaces. So like, let's say, for example, like R4, you're just going to find the dot product in R4. That is that you're going to multiply each component and then add them together. And that's going to be the same thing. So we're going to we've got let x equal, and essentially it's going to be x1, x2, all the way up through xn. And we'll let y equal y1, and again, y1, y2, and it's just a vector. And notice they have to both be of the same length. Can't find an inner product space, or excuse me, a dot product without actually having vectors of the same length, all right? The standard inner product, also called the dot product, is going to be written as x1, y1 plus x2, y2 plus dot 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 plus xn, yn. So we'll just multiply component y's, and we write that as x dotted with y. And that's our standard inner product called the dot product. Or sometimes we might write it like this. You'll see it written as this way. Okay, that is that it's written as, like, it's inside of a vector. The norm for this standard inner product is going to be the norm of, we'll call it x, and that actually equals the square root of the dot product with itself, x. Okay, so that may be something that wasn't actually emphasized, but that actually is exactly what it is. And so if you think about it, it's going to be the square root of x1 squared plus x2 squared plus dot 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 xn squared. And that is the norm for the standard inner product. So let's do an example. We'll first find the dot product of x and y, and then find the norm of x. We're going to let x equal -2, 0, 4, 1, -2, 0, and y equal 5, -1, -1, 6, -1, -3, 3. Okay? Notice they're both in R6. So this is x dotted with y will end up equaling negative 2 times 5 plus 0 times negative 1 plus 4 times negative 1 plus 6 times 1 plus negative 3 times negative, or negative 2 times negative 3 plus 0 times 3. So that's going to give me then negative 10 minus 4 plus 6 plus 6. And so that ends up equaling negative 2. We'll now find the norm. The norm of x is going to equal, it'll be the square root of negative 2 squared plus 0 squared plus 4 squared plus 1 squared plus negative 2 squared plus 0 squared. So that'll equal the square root of 4 plus 16 plus 1 plus 4. And that equals square root of 25, and that equals 5. And that's our norm. One thing to notice about the norm is going to always be positive in this case. We always have a positive norm. And so that's one of the reasons why, like, for example, in the case of the standard inner product space, it's so easy to define it as the distance because it ends up always being positive, right? It actually is the distance function, all right? And what we get here is we get, okay, so now that I have this defined standard inner product space, I can now actually utilize all of the stuff that I've got for vector spaces and everything that I've got that I learned in multivariable calculus with, you know, the dot product and finding, you know, relationships between figures in multivariable calculus, and I can use those, okay, because now I've got the machinery in order to be able to do that. So what we have now is we have, like, okay, so I've got the standard inner product, and what I want to do is I want to start to lay down some of the mathematical machinery in order to talk about the inner product spaces from the perspective of the standard inner product and give an example of why it is that we utilize them, and also how we're going to kind of be able to do some more rigorous mathematics using them. So for one thing, we're going to imagine we're going to let x, y, and z be vectors in Rn. So we're going to have vectors in Rn, all right, and let k basically is going to be k belong to the reals. That is, it's going to end up being a scalar, all right. And so this is going to help us to define our standard inner product mapping properties. So one, we're going to have that x dotted with itself is always going to be greater than or equal to 0, and we're going to have that x dotted with itself equals 0 only if x equals the 0 vector. Okay, this kind of makes some sense if you kind of think about this, right? If we have x as just being a standard vector in Rn, we have x1 times x1 plus x2 times x2, and these are not vectors, these are just components, plus x3 plus dot 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 xn, okay? And that will equal x1 squared plus x2 squared plus all the way up to xn squared, okay? Now, the idea here is that if, since our vectors are in Rn, the components x1 through xn are actually in Rn, okay? So x1 squared or xi squared is always going to be greater than or equal to 0, okay? And xi squared equals 0 only if xi equals 0. Okay, so that's the only way we're going to get that. So that dot product that we have there is going to be greater than or equal to 0, okay, for all x belonging to Rn. And we'll just add in a little piece here. We're going to say this is the dot product here of itself. So we can define that. All right. And so that's just a little mini proof, little sketch. Let's take a look at the second quality. Second quality is that yx equals xy. All right. So we have commutativity of the dot product. And that's kind of cool. It's pretty important. Remember that commutativity doesn't follow for, say, for example, matrix multiplication. That doesn't work. We can't just commute our matrices and I expect to get the same result. But in the case of the dot product, we can. And so, like, for example, if I write, I've got x dotted with y, that's going to equal x1, y1, excuse me, and these are not vectors. These are x1, y1 plus x2, y2 plus, and then we just go all the way down, plus xn, yn. And since x1 and y1 all the way down to xn and yn, they're just real numbers. So real numbers, you can actually commute their multiplication. That's not a problem for us. So this is actually going to end up equaling y1 x1 plus, and then remember addition, we can also, put an addition, commute addition with real numbers. So that allows us to do the same thing here. y2 x2 plus, and then go all the way down to yn xn. So basically just switch our values. And so that then is going to equal, well, that's equivalent to the dot product of y with x. Okay, so now we become more sophisticated mathematically. We do have to consider whether or not we have commutativity for our inner product space. Okay. Number 3. We have that if I take kx, so I multiply a vector times some vector k, y, that's going to equal, now be very careful about this, it's going to be k x y. Okay, which by the way is also equal to, if we wanted to, we could move the k over to the other value too. We could do this as well. That works. Okay? And you want to be really careful about this because it turns out that this, okay, so here's a note, that this kx, ky is actually equal to k squared times the dot product of x and y. All right? And you may remember that from your multivariable calculus class, you may not, but just be careful. Okay, that's a careful thing. And you know what? We'll just look at this. We could say, oh, okay, well, the dot product of kx with y is going to equal kx1, y1 plus kx2, y2, right? Because we're going to be just multiplying k by each value. That's what you do when you multiply, when you scalar multiply. Plus kx, and then plus dot, 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 right? Keep going until we hit plus kxn, yn. And that will then just equal k times x1, y1 plus x2, y2 plus k xn, yn. All right? And that's equal to k times the dot product of x and y. Notice that if I actually did this, what I get, at least just look at the first term, I get kx1, ky1, which is equal to k squared x1, y1. And I would do that for every term. And then what I'd end up with is I'd actually end up with kx squared, like I said, right? Take this note. So just be careful with that, okay? And here's a fourth property for us. And essentially what it is, it's kind of a distribution. We're going to have x plus y, comma z, right, is going to equal xz plus yz in terms of the dot product. So if I take x plus y dotted with z, it's going to equal x dotted with z plus y dotted with z. Okay, notice that this is on the right-hand side. Would it be the other way around? Would it be the same if we actually went the other way around? The answer is yes, because remember, we have commutativity of addition, or commutativity of our dot product. So that does work. But let's take a look at this one. So this is going to end up being, so I've got x plus y dotted with z is going to equal x1, y1, x1 plus y1, z1 plus x2, y2, x2 plus y2, excuse me, dotted with z times z2 plus, and then we go all the way down to xn plus yn zn. And this will then equal, and we look at this, it's going to be x1 z1 plus y1 z1, and then that'll go all the way down to xn zn plus y1 zn, or yn zn, excuse me. And then that'll end up being equal to, we'll just reorder, we can make this x1 z1 plus x2 z2, right? Plus dot 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 xn zn. plus y1 z1 plus y2 z2 plus, and then we'll go all the way down to yn zn. And what we're left with then is that this is, just as we thought, it'll be the dot product of x with z plus y with z. And there we go. And that actually ends up giving us our the qualities of our standard inner product space. All right, so kind of some important things to notice. Notice one, that dotting a vector with itself gives something that's always greater than or equal to 0. And it'll only equal 0 if x actually is the 0 vector. Right? That's going to tell us something important about our norm in the standard inner product space. One, we can commute the inner product. Very handy. Okay. Two, scalar multiplication, right, of a single vector, right, makes scalar multiplying by the dot product. Right? So only if you're scalar multiplying by a single vector. Otherwise, if you're pulling out, you're going to have to pull out twice. If, say, for example, it's the same k. Or if we had like k and j, two different values, you'll have to pull out both, so it'd be kj times x dotted with y. And then we can distribute addition over the dot product, which is actually very handy too. Okay, so some pretty handy qualities. All right, so now what we've done is we've gone in and we've kind of defined the inner product space. We've kind of defined some things that we can do on the inner product space. So we've now like combined our multivariable calculus class with our linear algebra class. We kind of brought them together, and now you can quit math. There it is. You're done. Right? No, I'm just kidding. Because math is like vast and still stuff to be done. So what we're going to be doing now is we're now going to actually generalize. So remember, we did like lots of stuff with vector spaces where we worked with polynomials. We worked in Rn. You actually could see it. We're going to see it where we work with functions. We're going to do some of that with our inner product space as well. And so what I want you to do is I want you to say, okay, cool. Now what I need is machinery for finding inner product spaces if it's just not a standard, inner product space in Rn. What if it's some other kind of inner product space? And it turns out there are a lot of them, right? As long as we have a set of qualities. So what we're going to do now is we're going to define the general definition of the inner product space. So we're going to let V be a real vector space, and we're going to take a mapping that associates a real number denoted as UV, okay, U dotted with V. And now here's the thing. U dotted with V doesn't necessarily mean that we have the standard inner product. It's only the standard inner product if we say it is, okay? It's going to be called an inner product, all right? If it satisfies the following properties for all u, v, and w, those are vectors, and all real numbers k, we have two things, or we have four things, excuse me. One, we have v dotted with itself is greater than or equal to 0, and v dotted with itself will only equal 0 if v is equal to the 0 vector. Okay, so we don't want to actually be able to take the dot product and end up with something negative. All right, and in addition to that, we don't want to end up with the 0 vector, or we don't want to end up with 0 unless we actually have the 0 vector. We basically, if you kind of think about it, we only want the only vector that has 0 magnitude is going to be the 0 vector. All right. All sorts of bad things can happen if that's not the case. All right, 2, we want that commutativity. We want UV to equal VU. That is, we're going to commute the dot product, or, commute the inner product, I should state. Then we're also going to want that scalar multiplication, KU, V, should equal K, U, and V. Notice, big time important, not the same thing as the process for scalar multiplication for vector spaces. Okay? It's a different thing with this inner product. And then 4, just like we had before, we're going to have U plus V dotted with W is going to equal U dotted with W plus V dotted with W. So that's going to end up becoming the values that or that's going to be what we have as our qualities, our properties for the inner product space. Okay? Then we'll define the norm. From that is going to end up being the norm of V is just going to equal exactly what we think it's going to be. It's going to end up being the square root of V dotted with itself. And again, we just don't want the norm to end up equaling 0 unless we're dealing with the 0 vector. Okay? And if it has all these qualities, then And we are defined on a real vector space. So that is Rn. Then V is called a real inner product space. And so that's what we're going to call it. We're going to call it a real inner product space. So let's take a look at an example. We're going to look at the inner product space for C0 a to b. And so what C0 a to b is the continuous functions on an interval a to b. And what we're going to do is we're going to define what the inner product actually is and then prove that in fact that what we do have is an inner product. So we'll define the inner product, right? We're going to define that we're going to take the dot product of f of x g of x, so that inner product of f of x g of x, and that's going to equal the integral from a to b of f of x times g of x dx. Okay, so that's going to be how we define it. And what's going to be interesting here is that mathematically, as long as what we have is we have something that follows the rules for our inner product space, they can be anything that we want. It doesn't really matter what it is, as long as it possesses those four qualities and the norm looks the way that we expect the norm to look. Okay, so what we're going to do is we're actually going to show that what we get here is we actually get an actual inner product space. So let's first consider the first one that we need is we need that f dotted with itself is going to be greater than or equal to 0 for all f. All right, that's the first one we need, and that the only way that we're going to get 0 is if f is actually the 0 function. So magnitude of f, or f dotted with itself equals 0 if f equals the constant function 0, f of x equals 0. So what we get is we're going to plug that in. We're going to plug f into this function. So it's going to have a to b, and it's going to be f of x squared dx. All right. Now, f of x squared is a non-negative function. All right. Okay. Because we're basically just taking f of x, multiplying it by itself. So we end up with a non-negative, also continuous function. Because if you multiply two continuous functions by itself, you end up with another continuous function. And so if we imagine, right, like what we're basically getting, if we take that integral, is, let's say, for example, this here is f of x squared. Okay? So there's the function f of x squared. Here's a, here's b. Okay? And since it's a non-negative continuous function for all values, right, because we're just squaring all the values of f of x, what we're looking for is we're looking for the area under the integral. Okay, basically we're looking for that area in there. That's got to be greater than or equal to 0. Okay, so basically we're going to see the picture there. All right, or essentially like just what I just said, right? If I take f of x squared, it's a non-negative continuous function, so every value is above the x-axis. We're finding the area from a to b, so consequently we're going to end up with a positive area. Okay. The other one, f of x equals 0, well, that's going to give me the 0. It's going to give me 0 because it's essentially, that's going to be this graph right there. It's going to be, there's going to be no area underneath that curve. So that's my first property. What about my second property? My second property is that f, the inner product of f and g, will equal the inner product of g and f. Well, properties of integral should tell you that that's going to be the case. I've got a to b, f, g, f of x, g of x, f of x times g of x dx. And that's certainly going to equal the integral from a to b of g of x, f of x dx by just our properties of integrals. Then third, we're going to need that kf, inner product with g, is going to equal k, inner product of f with g. And if we look at that, again, we're going to remember some things about integrals. I've got a to b, and this is going to be k f of x, g of x, dx. And remember, one of our properties of integrals is that I can pull out the constant. So this is now k times f of x, g of x, dx. Because I could just pull out that constant, allows me to do anything I want. And then 4, I need that f plus g, inner product with h, will equal FH plus FG, their inner products. And so if I take the integral now, I've got the integral from a to b is going to equal, or excuse me, integral of a to b of f plus g of x, h of x, dx. We know that this is going to then equal the integral from a to b of f of x plus g of x, right? Because that's how we add functions, times h of x dx. And then we can actually, that'll equal then the integral from a to b of f of x, h of x, plus g of x, h of x, dx. And then if we remember by our properties of integrals, we can just split these two up. This will give me the integral from a to b, f of x, h of x, dx, plus the integral from a to b, g of x, h of x, dx. Right? And so what you notice is I'm just utilizing the properties of, in this case, it's integration. Properties of integration, because how I've defined the inner product space is I've defined it utilizing integration. If, on the other hand, I define it utilizing, say, for example, like our standard inner product, right, where it's just multiplication and addition, you're going to use the qualities of addition and multiplication, you know, like the commutativity and the fact that you can add in any order and associativity, and like we could switch things around. And that allows me to actually go out and do this kind of proving that something, in fact, is an inner product space. All right, so let's suppose we want to let f and g belong to C0 from 0 to 1. So we're going to define this inner product space on just functions, continuous functions from 0 to 1. And this is actually something that happens pretty frequently. It turns out that defining things on just 0 to 1 is pretty equivalent to defining them on the entirety of the real number line. Just makes things a lot neater and tidier. And we'll define our inner product as being the integral from 0 to 1 of f of x, g of x, dx. So it's going to be that function inner product that we just looked at. What we're going to do now is we're going to find the inner product for f and x, where we define f of x equals 8x and g of x equals x squared minus 1. And we're also going to find the magnitude of f and the magnitude of g. So we'll start out by finding the inner product. And so that inner product, we'll call this the inner product of f with g, is going to equal 8x times x squared minus 1 dx, evaluated from 0 to 1. And so that'll then equal the integral from 0 to 1 of 8x cubed minus 8x dx. We'll go out, we'll find our integral then. That's going to be then 2x to the 4th minus 4x squared, evaluated from 0 to 1. Okay, and that'll then equal 2 minus 4 minus 0 minus 0. Okay, and so that ends up equaling negative 2. And that's the value for our inner product there. All right. Now, you might think to yourself, wait, it's not bigger than 0. That's okay. It's not the magnitude. It's the inner product. Okay, not the magnitude, it's the inner product. So this should be just fine. All right. Now, let's go in and actually calculate those magnitudes. These magnitudes should be greater than or equal to 0. So we'll take the integral from 0 to 1. So the magnitude of f is going to equal the integral from 0 to 1 of, and this will be 8x squared dx. And that'll equal then the integral from 0 to 1 of 64x to x squared dx, which equals 64 over 3 x cubed, evaluated from 0 to 1. And then we can see that that's just 64 over 3. And there's our first magnitude. Oh, but wait. I forgot. We do actually have to take the square root. It's going to be the square root of all of these ones. Square root, square root, square root, square root, and square root. So this ends up being 8 over the square root of 3. Okay, and that's my magnitude. So the magnitude of g then is going to be the square root of the integral from 0 to 1 of x squared minus 1 squared dx, which is equal to the integral from 0 to 1 of x to the 4th minus 2x squared plus 1 dx. And we'll take the square root of that. This is then going to equal the square root of x to the fifth minus 2/3 x cubed plus x evaluated from 0 to 1. So this is going to end up being 1 minus 2/3 plus 1, and then minus, essentially minus 0. And so that's 1 1/3. Or 4/3 in this case. But we're going to have to take the square root of that, right? Because remember, this is a magnitude. So this ends up being 2 over the square root of 3. And that's the magnitude of g. Okay? So essentially what we've done is we've utilized that norm, right? Which is the square root of the dot product of a function with itself. And that ends up giving us our magnitude. And then we can see our inner product, right? Our inner product is just simply the multiplication of those two functions. And then we'll take the integral along the bounds for our, in this case, vector space. All right? And that is actually how we find the inner product utilizing this functional space. So let's look at an example. Now what we want to do is we want to just talk about proving whether or not an operation is an inner product. So let's say, for example, we have the vector space P2R, and we'll have P of x be a0 plus a1x plus a2x squared. So basically a general polynomial or a second degree polynomial. And Q of x be b0 plus b1x plus b2x squared. And what we want to do is we want to define our inner product as a0 b1 plus a1 b2 plus a2 b0. And we want to know whether or not this is or is not an inner product. So what we need to do is we need to show, does it follow those four guidelines for an inner product space, right? We've got the four of them, that if we dot it with itself, it's going to be greater than or equal to 0, and then it only equals 0 if v is equal to 0, right? That we can commute the two, okay? That if we multiply by a scalar, u and v, that we get the scalar times the inner product, and we can distribute across addition. Well, let's take a look and let's consider a couple things. One, I want to notice that this is not, a0 b1, a1 b2, nothing like that, okay? So what I want to do is I want to see, okay, I want to know whether or not I can I get P of x dotted with itself, or inner product with itself, equal to 0 if P of x does not equal 0. So if I don't have a zero vector, if I don't have the zero vector. And the fact of the matter is you can. And a lot of that just stems with how we defined the inner product. So this definition of an inner product has caused all sorts of problems. So if we let, say, for example, P of x equal the constant function 1, okay? If P of x is equal to constant function 1, then for the first value, a0 equals 1, a2 or a1 equals 0, and a2 is equal to 0. And then since P of x equals 1 again, our b0 is now going to equal 1, our b1 is going to equal 0, and our b2 is going to equal 0 again. Okay? So now if we plug that into our formula, what I get is I get 0 times 1, or excuse me, yeah, I get 1 times 0 plus, and then this is a1 times b2, and so a1 is 0 plus 0 times 0 plus an a2 times b0, okay, and that ends up equaling a2 times b0, that ends up equaling 0 times 1, and that ends up equaling 0. So that's nice. That actually works out. Okay? But what if I chose two different vectors, okay? And I wanted to see inner product with itself negative, okay? And so what I'm going to do is I'm going to let P of x equal 2x minus 1. And so if I take P of x and dotted with inner P of x, that's going to be that my a0 will equal negative 1, my a1 will equal 2, and my a2 will equal 0. And then that'll also give me that b0 will equal negative 1, b1 will equal 2, and b2 will equal 0. So now I've got a0 b1. So a0 b1 is going to be negative 1 times 2 plus A1, 2 times B2 is 0, so 2 times 0, plus A2 times B0, so A2 is 0 times B0, 0 times negative 1, this equals negative 2. So what we've seen here is that, so P of x inner product with itself equals a negative number in this case, negative 2, so this is not an inner product. It actually does not fulfill the requirements for an inner product. Okay? And so there we go. You could actually go in and check for commutativity too, right? It'll also be the case that P of x, Q of x, right, does not equal Q of x, P of x. You can actually find a lot of different functions that will actually show that that's not the case, right? So what we have is it's not an inner product, and that doesn't work. A crucially important result that we get for inner product spaces is something called the Cauchy-Schwarz inequality. And this Cauchy-Schwarz inequality is going to play a big role for us when we start looking at projections. And so consequently, we're going to let U and V be vectors in an inner product space V. Then we get this result that the magnitude, okay, or the absolute value of the inner product of U and V is going to be less than or equal to the magnitude of U, or excuse me, the norm of U times the norm of V, right? And so if you kind of remember from your multivariable calculus class, we actually saw this before, right? Because cosine theta would be bounded by 1 and negative 1. So what we know is that the dot product is going to be always less than or equal to those two magnitudes, because it's going to be magnitude times cosine theta. So let's take a look and let's see actually how it is that we end up getting this result. Let's do a proof here to kind of help us understand a little bit better our inner product spaces. Okay, so we'll start out with we're going to let we'll have an arbitrary vector U plus KV. Okay, that is, we've got a vector U plus a scalar times V. All right, and what we know is that this 0 is going to be less than or equal to U plus KV. Okay, in magnitude, right? And this will then end up equaling U plus KV dotted with itself. And actually what we need to do, we need to square this. So that'll be equal to this. We know that this is bigger than 0. And then that is in fact what it's equal to, because that's the operation for the norm. Okay, so 0 is less than or equal to the norm of U plus KV squared, which equals U plus KV times U plus KV. Okay. Now we're going to do a little bit of work here. So this is then going to be U plus U plus KV U plus U plus KV KV. Right? And remember, that's because of our distribution. We've got this is an inner product, so we've got this defined as distribution. And then what this is then going to give me then is this is then going to be U dotted with U plus KV inner product with U plus U inner product with KV plus KV inner product KV. Again, that's our distribution property, the one that we saw before. All right, this thing here, this is going to be the magnitude of U squared plus, and then this is going to end up being K times V inner product with U plus K inner product with U and V, and that's just our scalars plus, and this is going to be K V magnitude squared. Okay, and again, what we've got there, all right, this is basically the definition of the magnitude, or definition of the norm, pardon me, not magnitude, of the norm, all right, and also that scalar factoring, if we want to call it that. That is that we could factor out the single scalar. then this is going to be the magnitude of u squared plus, and then this is k, and we'll rewrite this as u v because we can commute our inner product, k u v plus, and then this is going to end up being k squared magnitude v squared. Okay, and this is just, that's the commutativity. And remember what I said about the fact that if both of the vectors are multiplied by a scalar, it's actually going to be k squared when we pull it out. So we got the commutativity and the k squared. Okay, and so this is then going to be magnitude or norm of u squared plus 2k u inner product with v plus k squared v squared. So what I've got now is I've got u squared, okay, plus 2k u v plus k squared magnitude or norm of v squared, and that's got to be greater than or equal to 0. And so if you look here, what I actually have is I have a quadratic in k, right? K is just some arbitrary scalar. So what that means is that if I think about this, all right, using the quadratic, if I use the quadratic, I'm going to have that a equals the magnitude of v squared, b is going to equal 2uv, and c is going to equal the magnitude of u squared. Okay, just think about it, k being like my my variable, right? Or some arbitrary variable. And so, since that's going to be greater than or equal to 0, what that means is that my discriminant, and my discriminant is going to end up being, right, b squared, so 2uv squared minus, okay, 4 magnitude of v squared, magnitude of u squared, okay, must be less than or equal to 0. And the reason why is this, okay, if this, the discriminant, right, the discriminant of, if the discriminant is greater than 0, right, then this, okay, we'll call this number 1, okay, then 1 has 2 real roots. And so it would take negative values. But we can't have that. We can't have it take negative values, all right? Because what we've been told is that, in fact, this is greater than or equal to 0 at all times, so consequently it can never be negative. So consequently, this means that 2 inner product space uv squared minus 4 norm of v squared, norm of u squared has got to be less than or equal to 0. Now, what that means is that gives me 4, okay, and this will be uv squared, okay, is then going to be less than or equal to 4 magnitude v squared, magnitude u squared, okay, and so if I then divide through, okay, this is then going to be, we'll divide through by 4, divide through both by sides by 4, I get u v squared is then less than or equal to magnitude of v squared, or norm of v squared, norm of u squared. Okay? And then, if I take the square root of both sides, I'm actually going to end up with, I'm going to get uv, okay, is going to be less than or equal to magnitude of v, magnitude u, okay? But then also, don't forget, or rather negative, okay, if what I do now is I just say, okay, well, now I'll just take the square roots off, so I have to account for the fact that I'm going to have the absolute value. So the absolute value of uv is then going to be less than or equal to the norm of v times the norm of u. And that is our Cauchy-Schwarz inequality. So just a, kind of a proof to work through, to see kind of how we can utilize some of these, some of the parts of the inner product space, or some of the qualities of the inner product space. Also, to kind of see how clever you can be in terms of your math, this is an incredibly important result if you are studying mathematics. The Cauchy-Schwarz inequality is just huge. Okay? What is it? It's the magnitude, the absolute value of the dot product of two vectors is less than or equal to the norm of one of the vectors times the norm of the second. All right, so let's take a look at now an application of Cauchy-Schwarz, which is finding the angle between two vectors. So remember that we have the absolute value of u, inner product with v, is going to be less than or equal to the norm of v times the norm of u, or the other way around, either way. Okay? And so consequently, what this means is that if I divide through by uv, okay, then what I get is that this is going to be less than or equal to -1. So if I actually utilize this, I'm just going to see, okay, so if I take, I'll pull off the absolute values. So this is going to be u, v, okay, and I'll divide through by v, norm of u. That's either going to be less than or equal to 1 or greater than or equal to -1, all right? And depending upon the sign of uv, right? Okay, so depending on sign of uv. And so what we get here is we get the bounds for essentially cosine theta. So, or the value for cosine theta, right? So like what we end up with, and actually how it works geometrically if you work in the standard inner product space, is you end up that this is cosine theta. So cosine theta is then equal to the dot product of u, or the inner product of u and v, divided by the magnitude of v, divided by the magnitude of u. Okay, and that's what cosine theta is. And that's how we define the angle between two vectors, right? You've done that before inside of your classes. And we'll define this. We're going to have it, theta is going to be between 0 and pi. And that's how we'll define it. So like say, for example, if I let u equal the vector 1, -1, 2, 3, and v equal the vector -2, 1, 2, -2, then what I get is I'm going to get cosine theta, whatever cosine theta is going to equal the dot product. So that's going to be -2 plus -1 plus 4 plus -6 divided by, and then this will be the square root of 1 plus 1 plus 4 plus 9 times 4 plus 1 plus 4 plus 4. Okay, so this equals then, it's going to be -9 plus 4, so that's -5, divided by, and this is root 15 times root 13, which equals -5 over the square root of 195. Okay, so theta is going to equal cosine inverse of -5 over the square root of 195, which equals, in degrees, 110 degrees. So that should just be kind of a quick review on how to find the angle between two vectors. All right, we did that in multivariable, and there it is here. So now let's take a look at a set of inner product spaces that are really very valuable for physics and engineering, and that is the complex inner product spaces. We're going to have to do a little bit of gymnastics, a little bit of computational gymnastics, in order for us to, in fact, define the inner product here, but what you'll see is that it actually will end up working out very, very well for us. All right, so we're going to have first that Cn is going to be the set of n-dimensional vectors with complex components. So now we're looking at vectors that have complex components rather than just all real numbered vectors. We're going to define our inner product space as, if we have u, and these are all complex numbers, u1, u2, through un, and we'll define, say, for example, u1 as equaling a1 plus b1i, and we'll have v1 as equaling, say, c1 plus d1i, okay, for example, right, where we have an imaginary and a real component. Then our inner product space is going to be u1 times the conjugate of v1 plus u2 times the conjugate of v2 plus u all the way down to un times the conjugate of vn. So what that looks like is u1 conjugate v1, just as a little review, is going to be a1 plus b1i times c1 minus d1i. Okay? So that is that we're going to take the conjugate, which just means to make the addition sign in between the real and imaginary component into a minus instead of a plus, or basically switch the signs. And then our norm, the reason why we have to do this is to get that norm to be greater than or equal to 0. Remember that if you multiply two complex numbers together, you could end up with a negative number, right? The square of two complex numbers is a negative number. So instead, what we're going to do is we're going to say, okay, with this definition of the norm, with this definition, the norm ends up being the square root of v dotted with v, and so that ends up being v dotted with its conjugate, okay? And what we'll end up with is we're going to end up with a real numbered value, right? Well, v1 squared plus v2 squared plus all the way to vn squared. So let me kind of show you an example is probably going to help this out a little bit. So we'll let u equal 5 minus I, 3i, 6 plus 2i, and v equal 3, 2i, negative 1 minus 4i. Okay? So u, inner product with v, is then going to be 5 minus I, and then this is actually 3 plus 0i, so it ends up being 3 minus 0i. It's just going to be multiplied by 3. Okay? The conjugate of 3 is still just 3. Plus, and then this is be 3i, and then the imaginary part becomes negative. We'll switch the sign on the imaginary, so this ends up being negative 2i. Okay? Plus, and now 6 plus 2i times negative 1 plus 4i. Add those together, we get 15 minus 3i plus, or rather, minus 6i squared plus, and then this is going to be negative 6 minus 2i plus 24i plus 8i squared. So this is 15 minus 3i plus 6 plus, and this is negative 6 and negative 8, so plus negative 14 plus 22i. 15 minus 14 is 1, that's 7. And so this ends up being in the negative 3i plus 22i. So this is 7 plus 19i. And there is the dot product, right? Basically, like we said, we're going to take u, okay, or we're going to take each component of u, all right, and then multiply it by the conjugate of v. Go ahead and switch the order, see if you get the same thing. Turns out you will. All right. Now let's take u. Let's find the magnitude of u. Okay, the magnitude of u, and that's going to end up being then the square root of 5 minus I times 5 plus I plus 3I times negative 3I plus 6 plus 2I times 6 minus 2i. Okay? What's going to end up happening, you'll notice, these are all differences of squareds. So this is going to be 25, and this will be minus I squared. But I squared is negative, so it's minus a negative, so it's going to be plus 1. Plus, and this will be negative 9I squared, which again is going to be positive, plus 36 minus 4I squared. We'll take this in square root. So this is going to be the square root of 25 plus 1 plus 9 plus 36 plus 4. So this is 49, 50, so this is equal to the square root of 75. All right, so what we need to do now is we have a little bit, because we're using that conjugate inside of our definition for the inner product, for the complex inner product space. What we have to do is we actually have to go in, we have to redefine just a little bit of our conditions. And what you'll see is actually these conditions are exactly the same for the reals, okay? But what we've done is we've done a practice that we do in math all the time. We've expanded it out now to include the complex ones. So the rules are still the same for the reals. This is actually the same set of rules for the reals, okay, if we kind of adapt them to real numbers. But now it actually allows us to have inner product spaces for complex numbers as well, or complex vectors. So again, we've got v. The inner product of v with itself is going to end up equaling, is going to be greater than or equal to 0. And we also have that v inner product v equals 0 if and only if v equals the 0 vector. So that's the only way that that's going to happen. All right, vu equals, now this is going to be the conjugate u, this is u and v, excuse me, u inner product v will equal the conjugate of v inner product u. All right, so basically what we do there is, say for example, you've got u1 v1, right, plus u2 v2. Well, and then we're going to take the conjugate there. This is going to equal, actually, if we take its conjugate, we get u1 v1 plus u2 v2 conjugate, and then we conjugate it. This ends up giving me u1 conjugate v1 plus u2 conjugate v2. Okay? And so consequently that ends up being vu. This is the primary difference that we have there. The other condition for number 2 would not hold for complex inner product spaces. We've got our scalar multiplication, and we've got our distribution, and then finally we have what our norm is. Our norm here is going to be the norm of v is equal to the square root of v inner product with v. And so that kind of completes us out for inner product spaces. The truth is like the stuff that you're going to do with inner product spaces, not too difficult. It's just calculation, really, a little bit of integration, nothing too terrible, a little bit of integration, but pretty standard stuff. Otherwise, it's going to look a lot like functions of real variables. It's the kind of thing that you did probably in your multivariable class, all right? So that you can kind of improve. Well, yeah, and so it should look like a bit of a review from that perspective. All right, we've just extended this out just a little bit. There's some work with proving that something's an inner product space or proving that it's not one. And so we want to kind of like dive a little bit deeper into the theoretical part. But hopefully you find this to be pretty familiar stuff.